We're on the unit about the gas laws. We've taken the combined gas law and broken it down into its components, Boyles, Charles, and Gay-Lussac. We also have talked about the ideal gas law. Let's review each of these. On the quiz, as with the test, you'll be asked to not only solve the problem, but analyze which gas law it refers to, the relationship within the gas law, and to do some critical thinking like reporting your answer to the correct number of significant digits. There is a method to the madness. Begin with writing down all of the given information. In this problem, it says the volume of a gas at 2.5 atmosphere was measured at 35 milliliters. What will be the volume if the pressure is adjusted to STP? So let's write down the given information. Since the new pressure is at STP, we'll record P2 as 1 atmosphere. In order to figure out which equation we need to consider what our given information is. We have volume and pressure, and we're asked to find a volume. The part of the combined gas law would be pressure and volume. That would be Boyles' law. Rearranged to solve for volume, it will be pressure times volume divided by the new pressure. So we get 87.5 milliliters as our answer. Since the given information was in 2 significant digits, we want to round this answer to 2 significant digits. The relationship between pressure and volume, according to Boyles' law, is an inverse relationship. As the pressure decreased from 2.5 to 1 atmosphere, the volume increased from 35 milliliters to 88 milliliters. This example reads, a sample of gas has a volume of 150 liters at 60 degrees Celsius. To what temperature, in Kelvin, must the gas be lowered to reduce the volume to 50 liters at constant pressure? There are a couple of clues within the question. First, temperature will need to be converted to Kelvin. And second, since pressure is held constant, we won't use pressure. We will only concentrate on volume and temperature so we can figure out which gas law we're dealing with. The gas law concerned with the relationship between volume and temperature is Charles' law. According to this question, we can anticipate a drop in the volume as well as a drop in the temperature, demonstrating the direct relationship between volume and temperature in Charles' law. Since the equation is V1 over T1 equals V2 over T2, and we're needing to solve for T2, we'll have to do a little bit of algebraic magic. Let's start by flipping the entire equation upside down. Now solving for T2 becomes a simple matter of multiplying V2 by both sides. Substitute in, and then solve. Of course, you'll want to report the answer to the proper number of significant digits. In this case, we need to round 111 to 1 significant digit, which would be 100. This one says, a sample of gas at 50 degrees Celsius exerts a pressure of 270 millimeters of mercury. If the gas is heated to 80 degrees Celsius at constant volume, what is the new pressure of hydrogen? So we're dealing with something that has pressure and temperature. Let's refer to the combined gas law to figure out which gas law this is. The relationship between pressure and temperature of a gas is Gay-Lussac's gas law. This is a direct relationship. And since we can see from the data that the temperature increases, we can anticipate that the pressure will also increase. Notice all temperatures are converted to Kelvin. We substitute in and then solve. The answer of 295 millimeters of mercury rounded to one significant digit, would be 300 millimeters of mercury. It says, what pressure is ideally exerted by 0.5 moles of gas in a 4-liter container at a temperature of 300 Kelvin? A couple of context clues here. It mentions number of moles, and it also cleverly uses the word ideally. We can predict that this is going to be an ideal gas law question. The equation is PV equals NRT, where N is the number of moles, V volume, T temperature in Kelvin, and we need to solve for P. We'll need to use the ideal gas constant R. Because it does not specify what unit, we get to choose. There are two possibilities. This problem can be worked using either 62.4 millimeters of mercury liter per mole Kelvin or 0.0821 atmosphere liter per mole Kelvin. Because it doesn't specify, you get to choose for yourself which one you want to use. In this example, I chose to go with the 62.4 millimeters of mercury liter per mole Kelvin to solve the problem. Therefore, my final answer is expressed in millimeters of mercury because that's the unit of pressure in the R value of 62.4. If you work it in atmosphere, the answer is 3 atmosphere, which is consistent with converting 2,340 millimeters of mercury to atmosphere by dividing by the standard of 760 millimeters of mercury. This is the ideal gas law. I hope that running through some sample problems helps you to prepare for your gas law quiz.